So I will have a short comment on our previously discussed material, which actually is some concept of potential in uniform electric field. And then we will proceed further with the analysis of potential and potential difference in the field created by a point electric charge. So let me start. We mentioned last time that in case of a uniform electric field, it doesn't matter how there's no difference in terms of work to be done and in terms of changing the potential if we move from point A to point B or point C. So that means that there is some surface with equal potential, which is aligned perpendicularly to the electric field lines. And this surface is called equal potential surface. And it's kind of useful concept to represent, like an option to represent electric field in terms not of electric field lines, but also in terms of a set of these equipotential surfaces. And the feature of this surface is that if we move some test electric charge within this on some path which goes on equipotential surface, means that any work by electric field is not done, and there is no change in electrostatic potential. So only when we move from one equipotential surface to another, then some work should be done, because there will be always some voltage, like potential difference between these two surfaces. Okay, so now let us go to new slide, and we will start analyzing the electric potential and potential energy of a system point charge, probe charge, and try to understand how electrostatic potential is changing in the electric field created by a point charge as a source charge. So let us show here some positive point charge with charge Q. And then let's say we have two points, will be point A, point B. We can set the position of point A with radius vector, or like position vector R, A. Then there is some path from point A to point B, and position of point B can be described by position vector RB. Okay, so in this case, we can divide our path to some very small displacement vectors, and let's show it. Here will be ds vector. Then here we have some intermediate position vector R. Then this will be our R unit vector. So it will just define the orientation of our position vector, so intermediate position vector. And here we will have some angle theta between the displacement vector ds and position intermediate position vector r, or the unit vector r. They have the same orientation. And this will be projection of our displacement vector on the direction of the intermediate radius vector or position vector. And that's why this will be dr, change of the position vector r. So now let us try to calculate the difference in like potential difference between points A and B. So potential difference between points A and B. So it's like difference between potential at point B and potential at point A will be equal, as we discussed earlier, minus integral from A to B, scalar product of electric field vector and displacement vector ds. Since it's a point electric charge, so we know how to write the electric field to determine and define electric field vector at any position in space around this electric charge, point electric charge. So this is Coulomb's law. We have Coulomb's constant times Q, which is electric charge, divided by R square. It's radius, like distance from this point where we want to determine electric field vector, times R unit vector. So which gives us the direction. Only direction doesn't affect on the magnitude of vector E. So now we can express this scalar product. Will be E vector times ds vector will be equal. So instead of E vector, we can substitute its value. Will be constant Ke U R square R unit vector times ds vector. Now let us take a closer look on this product. So we have unit vector R times ds vector. Yeah, it can be represented, since the unit vector has obviously unit magnitude, then this product will be equal to ds, the magnitude of vector ds, times cosine theta, the angle, cosine theta, this angle between unit vector, unit radius vector, and the displacement vector. And this is nothing else, as you may see from this triangular, as change of the radius, intermediate radius vector. So it's kind of projection of vector, displacement vector on the direction of unit radius vector. So it will be dr, change of the position vector or radius vector, while within this very small displacement, which is described by displacement vector ds. Taking this into account, we can write now that this product, scalar product, will be equal to Ke Q divided by R squared. And instead of this scalar product of unit vector R ds vector, we will substitute dr. Okay, so here I made a mistake. Vector should not be here because we have the scalar product, and scalar product gives us scalar number. So it's just magnitude of the change of position vector dr. And now we can proceed with the calculation of potential difference, which we want to know. So VB minus VA will be equal to minus KEQ. These are constants. We take them, factor them out from the integral. Integral from RA to RB, so position vectors at points A and B, dr over R squared. And then we will have, after integration, KE Q over R from R A to R B. And our final equation, which describes this difference in potential, will be KE times Q 1 over R B minus 1 over R A. So this is the equation how we can calculate difference in potential between 2 points located in space around a point charge. And now, since it's potential field, we can arbitrarily define any point which is considered to be with zero potential. So usually for these cases, it can be any point arbitrarily chosen, but makes sense to consider a point which is located at infinity from this charge. Its potential will be equal to zero. So if we want now determine the potential, not difference in potentials, but potential of any point next to a point charge, then we can use such equation. So potential will be KE Q divided by R. So why? Because we had this KE Q 1 over R B minus 1 over R RA. If we assume that RA is infinity, if we move from infinitely far from point charge, which is the source of this electric field, which we investigate, and arrive in some point which is close to this charge, then if we divide 1 by infinity, we will get 0. And this will be kind of potential difference between the point B and infinity. So actually it will give us absolute value of the electrostatic potential in this point in the framework of that system where we arbitrarily select that every point which is infinitely far from the point charge possess electrostatic potential equal to 0. Okay, so with this we are done. So now we need to consider an option when we have a system of charges. And in that case, we can also calculate the electrostatic potential of given point. So if we want to have some effective electrostatic potential originated from different point charges, which are sources of electric field, then we need to sum up all potentials caused by each of these charge in this given point. And this is necessary to underline here that finding some equivalent potential of a system of charges in the field originated from a system of point charges is much easier than finding the equivalent electric field vector created by system of point charges, because here we deal with a scalar quantity, and that's why we just have algebraic sum of scalar numbers. Instead, for the electric field vector, we need to deal with the sum of vectors, which is definitely more time-consuming and complicated. So if, for instance, we have some, so far we were talking only about electrostatic potential, which is, as you remember from previous lecture, is a feature of electric field itself. So we don't need any test charges to operate with this concept. However, we also have potential energy, and if we have some test charge Q naught, and we place it in a point of space next to the point charge Q with potential V, then definitely it will possess the system electric field test charge Q naught will possess some potential energy. And this potential energy U can be expressed as the Coulomb constant times Q naught times Q divided by R, which is the position vector which defines location of position of test charge with respect to the source charge Q. So this is the equation for potential energy, which already takes into account features of the field in this point and also features of the test charge. If we deal with electrostatic potential, that's only feature of the field. Also, if we have some system of charges, each of these charges create electric field around itself, and neighboring charge could be considered, or system of charges could be considered as test charges. That's why if we want to calculate the potential energy of whole system of charges, we need to consider like sum up potential energies of each pairs of electric charges involved in this system. So as an example, let's say we have charge Q1. Let's say we have all positive charges. Q2 and Q3. So there are certain distances between these charges. Will be R12, R23, and R13. So in this case, when we need to calculate potential energy of such system of charges, we follow such an equation, which is Coulomb constant times Q1 times Q2 divided by R12 plus Q2 times Q3 divided by R23 plus Q1 times Q3 divided by R13. So it takes into account contributions of potential energies of each pair of electric charges which are involved in the system. So by summing up, we will calculate the total potential energy of this system of electric charges. Okay, at this point, we proceed further and try to understand the relationship between electrostatic potential and like distribution and electric field. So far, we were calculated electrostatic potential from knowing electric field vector distribution, but it is also possible to go backwards. And if, for instance, electrostatic potential distribution is given, it's possible to extract all information about electric field vector. So let us consider a system like some electric field vector which has only one component along axis x. We have axis x, and this is our electric field vector, and it has only one component, like projection of on axis x, Ex. So in this case, this product, scalar product, which we were working with, of electric field vector to some displacement vector, can be replaced by a product of x component of this electric field vector times dx. And obviously that displacement vector is also aligned in the direction of axis x, so they are parallel, and we don't have any angle between these two vectors. So in such system, we can write that small change, like difference in electrostatic potential, dV, would be equal to minus Ex times dx. And from here, we can show that Ex, the electric field vector x component, is equal to minus dv over dx. So it's actually minus derivative of electrostatic potential over x. So kind of rate of changing of electrostatic potential along direction of axis x. So if, for instance, we have some potential surface, and this the path which we choose is going along this equipotential surface, then we know that from definition that it possesses the same potential at each point of this surface. This derivative will be equal to 0, dv over dx equal to 0, or because it doesn't change, we change dx, like move along the surface, but dv is equal to 0. So, or in other words, dv is equal to minus e vector times ds vector, and this will be equal to 0. So by definition, we don't have any change of this potential along the equipotential surface. So in other system, when we have some symmetry of electric field, let's say we deal with electric field originated from a point charge, we have some spherical symmetry, then it's more convenient to use equation to use the relationship between electric field and potential in the system of coordinates which attach not to some axis but to the change of radius vector or position vector, which is defined position of this point with respect to the source point charge. So in this case, we can write that E vector times ds vector, what we actually did earlier this lesson, is equal to E in the direction of r times dr, and this will be equal to the change of potential. From here, we can write the electric field in the direction of r, which is very convenient for the spherical system. Symmetry of electric field is equal to minus dv over dr. So like derivative of electrostatic potential along the direction of radius vector, position vector. So taking into account that we know now equation for the electrostatic potential in such a field created by a point source charge, it will be Ke times Q divided by R. So from here, we can take this derivative, and it will allow us to get the expression for the electric field. And let us go and do this. So minus dv over dr is equal. So we have minus this here. Then we have, when we take derivative, we have 1 minus 1, and it will be K E times Q divided by R squared. So minus and minus will give us plus, and we will end up with a E Q R squared. And this is nothing else as the Coulomb equation, which describes electric field next to a point charge. So by reversing this task, by taking derivative of electrostatic potential in the direction of position vector next to a point charge, we can go from potential electrostatic potential distribution to the distribution of electric field or electric field vector. This is kind of very useful approach because, as I mentioned before, when we have some complex system of electric charges, it's much easier to calculate electrostatic potential distribution, like set, it's so-called set scalar field of electrostatic potential in the space around this complex system of charges. And then using this scalar field, we can take the derivative of this scalar field and calculate a vector field, which is electric field vector distribution in the space around this point electric charge. So that is how is the way how it's really straightforward to do, because other way around it may be quite difficult to calculate directly electric field vector. However, as you understand, it's not always we have some symmetric cases or some electric field aligned parallel to some axis. So when we operate with scalar field of electrostatic potential and vector field of electric field vector, we usually operate in the three-dimensional case, and that should be taken into account. So let's say if electric field in general case is given by some function of x, y, and z, so it's three-dimensional distribution, then we can determine each component, x, y, and z component of this electric field vector by taking derivatives, like partial derivatives of electrostatic potential change along this along these directions. So it means that Ex component will be equal to minus dV over dx, as we mentioned before. Then Ey will be equal to minus dV over dy. So keep in mind these are partial derivatives, so we take derivative specifically with this variable x, y, and z. Z will be equal to minus dV over dz. And while we take these partial derivatives, other variables which are not in the denominator, they are considered as constants. So this is the rule how you take partial derivatives. And then it's possible to, in general, to express electric field vector as minus this like flipped triangular times V. So this is a gradient operator. So gradient operator is operator which defines the magnitude and direction of the gradient of scalar field V. So it's also three-dimensionally distributed X, Y, and Z scalar field. So each point in three-dimension around in the space, three-dimensional space around certain system of charges are given specific scalar quantities, and these scalar quantities are electrostatic potentials. And by applying this gradient operator, so this gradient operator is can be represented in more like clear form. So it's just this flipped triangular is just a short form. So in full form, it will look like this. It will be negative. Obviously, it takes into account all these derivatives along three directions, like partial derivatives along three axes. But also, since it's gradient operator and gradient is a vector, and this vector is always aligned in the direction of the fastest change of scalar field, in our case is electrostatic field distribution. So we also need some unit vectors which specify in which direction these derivatives are taken. So that's why we have I, unit vector along axis X, d over d x plus j, unit vector along axis Y, d over dy, and plus k, unit vector along axis Z, times d over d z, and we can factor out our three-dimensional electrostatic field V, X, Y, Z. So that is actually how we determine electric field vector in three-dimensional case when we have three-dimensional scalar field which defines distribution of electrostatic potential. We take partial derivatives and they define respective components of electric field vector along axis X, Y, and Z, and these directions are defined by these unit vectors. And their magnitudes, like projections of the electrostatic vector on given direction, is defined by these partial derivatives. Okay, so this is explanation of relationship between electric field and electrostatic potential. So we started initially from finding electrostatic potential from known electric field, and now we discussed, explain how we can go backwards and determine electric field vector from scalar field of electrostatic potential distribution in space. So now probably let's do some, let's consider some case of calculating or performing these calculations of electrostatic potential of a system of two charges. So let's say we have some system coordinates X, Y. We have two charges which can be called such system of two charges, be called as dipole. So we have one positive charge Q and one negative charge minus Q. They are equal by magnitude, but different by sign. So they are located with respect to the origin of the system of coordinate, the distance equal distances A. And our question is, first of all, we are interested in this point P, which has coordinate Y. We want to know the electrostatic potential in this point. And then second will be, we will work with point R, which is located at some on this axis X at the distance X from the origin of the coordinates. So let's say first question we want to answer, what will be electrostatic potential in at point P? So we remember, so we have a system of two charges, and we remember this equation like superposition of electrostatic potentials. Okay, E times sum over all charges, QI over RI. Okay, so let us do this. So this will be KE. We have two charges. That's why we will have contributions from both of them. Will be Q, and here RI is like distance from the point where you want to determine the electrostatic potential to the point charge, which is source. So in this case, this distance, it will be square root of A second power plus Y second power. So it's kind of the from right triangular, we can determine the hypotenuse of this triangular. And so this is for positive charge, and this plus, and we have one negative charge. So it will be minus Q, and the same distance because they are symmetrically located with respect to the point P. PA squared plus Y squared. And since the magnitudes Q is equal plus Q by absolute value is equal to minus Q, we see from here that we get 0 because they kind of cancel each other. So because of the symmetry of the location and equal charges but different signs, they cancel each other, and electrostatic potential at this point will be 0. So now question number 2, which we would like to address, is what will be electrostatic potential at point R. So here we again need to sum up, but it will be a bit different because they are already not symmetrically oriented with respect to point R. So here VR will be, question, will be equal, again, this superposition, Ui over Ri, and this will be Ke times Q divided, what will be the distance between positive charge and point R will be X plus A. So X plus A. Then will be plus. We have negative charge Q, which is on the right side from the origin of the system of coordinates, and that will be this difference between x and a. X minus a. Okay, so let's take into account this sign of this negative charge and factor out q because it is the same for positive charge and negative charge times 1 over x plus a minus 1 over x minus a. And now when we set to common denominator, we will have k e times q x minus a minus x plus a divided by x plus a times x minus a. And this will be a e q times minus 2a oh no, so here it's minus because we opened the parentheses. So it will be this and this cancel, minus 2a x squared minus a squared. And finally, we will get that potential at point R is equal to minus, let's check again, k equal to times 2a, okay, will be 2a k e q divided by x squared minus a squared. Okay, so this is the final expression for the electrostatic potential at point R, which is located along axis x at distance x from the center of this dipole created by positive and negative charges q and aligned along this axis x. Now the question is, we would like to determine the electric field at this point. So let's do it. We started a bit earlier. Let's spend a bit more, a few minutes to finish this. So let's calculate the electric field component Ex at point R. And for this, we need to consider that X, let's say this point where we want to determine electric field is located much further from the dipole than A, like distance of the charges to the origin of the system of coordinates. So if now we consider this equation, assuming that x is much larger than a, then obviously x squared is also much larger than a. And that's why we can simplify it. So it will be minus 2k e q a divided just by x squared, because in this case, assuming this condition, x squared, we can neglect with a squared because it's much smaller than x squared. So, okay, now we have this equation for electrostatic potential next to, at this point, which is located very far from the dipole. along axis X. And in order to calculate this X component of electric field, we take the derivative. So it will be minus dV over dx. It will be minus d over dx. And here we have our equation for V. So will be 2ke qa divided by x squared. So now the derivative, we can take out from this derivative sign the constants. So it will be and also we can get rid of these two minuses. So it will be 2k e q a, all these are constants, times d over dx, and our function which we will differentiate, it will be 1 over x squared. And when we take this derivative, it will be minus 4 ae qa divided by x cubed, assuming that x is much larger than a. So this is the way how we go backwards and determine electric field in practice when we know equation for the electrostatic potential, take derivative, and determine, get expression for the electric field in this point of interest. Okay, I think that definitely we are out of time today already. And thank you very much for attention. We will proceed further with determining electrostatic potential and electric field vector from electrostatic potential for some continuum charges distribution, and that will be already next time on Wednesday. So hope you are doing well by then. Try to work with the textbook. Don't forget about textbook. And if you have questions, you're welcome to ask either now or on Wednesday. Don't hesitate to ask questions. Good. Thank you very much for attention and have a good evening. Bye-bye. Bye.